series solution of this differential equation, we're going to let y equal a subscript n times n to the x. Now, excuse me, that's not quite right. Switch that around a little bit. That's a to the n x to the n. And now we can find y prime from that. Actually, no, this is a series solution. So this summation from 0 to infinity of this is our series. Now y prime here is going to be the derivative of this. This is again going to be a summation from 0 to infinity. But now it's going to be n, taking this n down, times a to the n, x to the n minus 1. See? And then finally, y double prime is going to be the derivative of this. So it's going to be the summation from 0 to an infinity of n minus 1, taking it down from there, times n, times a to the n x n minus 2. Now this is all well and good. Except, excuse me, this isn't quite right, because it needs to start a little bit further out there. This is from 1 to infinity, 2 from infinity, and the issue that we're running into here after taking the derivative, these are not starting from the same spot. So before we can write this again, the differential equation, we need to modify the starting place of this series. So we're going to change this, and we're just going to start from 0 and add 2, or substitute n plus 2 for n in all these places. So y double prime, we can also write as 0 to infinity. N minus 1 plus 2 is n plus 1. N, substitute that n plus 2. A to the n plus 2, see, times x to the n. And now rather conveniently have x to the n here, x to the n here. So we can rewrite this differential equation as y double prime plus y equals 0 is going to become the summation from 0 to infinity n plus 1 times n plus 2 a to the n plus 2 x to the n plus, that's the y double prime, y, which is a to the n x to the n. And from here, we can simply redistribute this and rewrite it by taking out the x to the n plus 1, n plus 2, a to the n plus 2, subscript there, plus a to the n, and all of that times x to the n. Now, x to the n we're going to ignore just for right now, because we're doing centered around x0 equals 0. So this we're just going to say is 1. And for this to equal 0, x to the n is going to always be 1 if n is 0. So this must be 0 for that to equal 0. So we could write this as n plus 1 times n plus 2, a to the n plus 2. or not 2 of it, subscript, plus a to the n equals 0. And since we have this equality, we can now start putting things on the other side. N plus 1, n plus 2, a to the n plus 2, equals negative a to the n. And finally, we divide both sides by n plus 1, n plus 2 to find a to the n plus 2 equals n plus 1, no. This is our denominator, sorry. Negative a to the n over n plus 1, n plus 2. And now that we have this, we can write the first few terms of this series. So let's take n equals 0. For n equals 0, we're going to have a to the 2. N equals 0, n plus 2, or 0 plus 2 is 2. So for that, a2 is negative a0 over n plus 1, n plus 2. That's 1 times 2. And then next, let's say n equals 1. We have a3 equals negative a1 over 2 times 3. And then we continue with n equals 2, with a4 equals negative a2 over 3 times 4. And then something rather curious happens, you see, because we already know what a2 is. So instead, we can write this in terms of a0. So that's negative a0 over 1 times 2, all over 3 times 4, which equals rather negative a0 equals, and you can simplify this to a0 over 4 times 3 times 2. And if you continue here to n equals 3, you find a subscript 5 is equal to negative a3 over 3 4 times 5. But just like we went back up to look at a0, we can see that we already know what a3 is. And a3 is negative a1 over 2 times 3. So we can rewrite this as a1 over 5 times 4 times 3 times 2. And we can keep going on like this until we find that we're alternating between terms that have a0 on top and terms that have a1 on top. And so eventually what you're going to find is that you can write this as a0 times and we can't forget about our x of n here. So when we read our series, our first a0 term is n of 0, so that's just 1. And then our next a0 term is here. we have a visitor.
Where's Sean at?
Next room. Plus x squared plus x to the fourth plus x to the sixth. And that's 0, 2, 4, 6 are our powers. And this is over 1 factorial. This is over 2 factorial. This is over 4 factorial. And this is over 6 factorial. And you'll see the pattern here is 1 times 2 is 2 factorial, 3 times 2, and then times 1 is 3 factorial, 4 times 3 times 2 is 4 factorial. And it continues on that. We have, this is in fact 0 factorial, which in fact equals 1 factorial, but not quite the same thing. And over here we have terms we can write in terms of A1, which is 1 factorial, or x over 1 factorial, plus x to the third over 3 factorial, plus x to the fifth over 5 factorial, plus x to the seventh, 7 factorial. And if you're familiar with Maclaurin series, which are series like this that are centered around 0, you may know that this equals cosine of x, and this equals sine of x. And this makes sense because if we look at our original differential equation, we're looking for something, if you take the derivative of it twice, it equals the negative of what you originally have. So you take cosine x, for instance. If you take the derivative of that, that's negative sine x. If you take the derivative of it again, you get negative cosine x. Cosine x plus negative cosine x is in fact 0. You do the same thing with sine x. The derivative of sine x is cosine x. And if you take the derivative of that again, it's negative sine x. Negative sine x plus sine x is again 0. So we see that this solution makes sense. By finding the series solution of this differential equation around x0, or the Maclaurin series, we see that we can find a solution to this problem using series. The sum of this, which we can also write as C1 times cosine x plus C2 sine x, is a solution to this differential equation because it is a sum of two solutions. And that about wraps it up.